All right, welcome back to another calculus lecture. In today's lecture, what we're going to do is conclude our study of the derivative and its applications with with this really sort of neat technique for evaluating certain limits, known as L'Hopital's rule. This is actually, it's a French name. This is an Anglicanization of his name. I believe it would have actually been pronounced like Le Hospital, like lay hospital, literally. Don't quote me on that. I'm actually not sure, but a lot of people, jokingly refer to this as lay hospital's rule. So anyways, what is L'Hopital's rule? So perhaps maybe to motivate L'Hopital's rule, let's consider, let's go back to, computing limits for a moment and look at a particular limit. So let's compute the limit as x approaches 0 of e to the 2x minus 1 over x. Okay, well, the first thing we always try with limits is just directly substitute the point that you're approaching in the limit. So let's go ahead and just try and plug in x equals 0. So what do we get here? Well, maybe I won't write that there. So limit as x goes to 0 of e to the 2x minus 1 over x is equal to, well, if I plug in 0, I get e to the 0, which is just 1, minus 1, which is 0, divided by 0. And more, so, when we looked at limits, we had a few ways of handling things like this. When we had 0 over 0, we could factor functions and sort of see how these polynomials simplified a little bit. But here I have like e to the power of 2x, and I don't really know what to do with that. I can't factor it anyway. So how do I compute this limit? Well, maybe let's look graphically at what this should look like. So, question. How do we compute this? And Bernoulli's idea, the guy who actually came up with this rule, and then L'Hopital, he was the Marquis de L'Hopital, and he was writing a calculus textbook, and he knew one of the Bernoullis. Bernoulli is a family name of a bunch of mathematicians. He knew one of them, and he knew of this result, and he's like, hey, can I buy that off of you? And he literally bought the rights to this result, this mathematical theorem, and it now bears his name. It was actually proved not by L'Hopital, but by one of the Bernoullis. Interesting history there. I really am a full-service instructor, history and mathematics. So what was Bernoulli's idea? Bernoulli's idea was to look at linear approximation. So recall that, well, first let me write that down. Look at linear approximations. And so the idea is to note that if a function equals 0 at a certain point, so if f of a, so a here is just going to be a number, if f of a is equal to 0, so we happen to be passing through a root at this particular point, then f of x is approximately the tangent line approximation at that point. But notice the plus f of a that's normally right here, when we write down the tangent line approximation, well, f of a is just 0, so we don't have to write anything down. So if this is true, then f of x should be approximately this function for x near a. Well, when we're doing limits, the whole idea is to think about values of x that are near the point where we're taking the limit. And so if we take this idea and run with it, let's maybe go ahead and look at this limit with this perspective. So with this perspective, let's just give names to these functions. F of x equal e to the 2x minus 1, and g of x is just going to be x. And let's go ahead and compute the tangent line approximations. So for x near 0, we compute the tangent line approximations for each of these. Well, g of x is real easy. It is its own tangent line. It's just a line. So it is equal to its tangent line everywhere. And for f of x, we have that for x near 0, well, I need to compute the tangent line, so this is going to be, it should be approximately equal to the derivative at 0 times x minus 0. And what is the derivative here? So maybe come off to the side and do some scratch work. F prime of x is equal to, I apply the chain rule and I get the derivative of e to the 2x is just 2e to the 2x, and then the minus 1 just goes away when you differentiate. So, and then if I take and I evaluate this function at x equals 0, well, the e to the 0 goes away. That's just 1. So I have that f prime of 0 is 2. So this should be equal to 2. That's my f prime of 0. And then x minus 0, well, that's just x. And so for x near 0, f of x is approximately equal to 2x. Okay? So thus we expect that the limit as x approaches 0 of e to the 2x minus 1 over x, well, this is equal to the limit as x goes to 0 of, I just put in these functions that I gave names to, so f of x over g of x. And now I'm going to replace this limit with the tangent line approximations, because f of x should be approximately behaving in this way, same thing with g of x, and so the limit should see that. The limit focuses on local behavior, on the behavior around the point 0 in this case, but more generally just the point you're approaching. So we should be able to sort of say that the limit should be this. So this is going to be approximately equal to f prime of 0. And we'll go ahead and write this out in full. So if I were to write down the tangent line approximations in each case, then, you know, this is exactly what I have. The slope, and then x minus the x coordinate, plus, I normally have a plus f of 0 and a plus g of 0 in the numerator and the denominator, but because those are equal to 0, in this specific example, those don't exist. And so this is going to be the limit as x approaches 0 of f prime of 0 over g prime of 0. And then notice what happens. F prime of 0 we said was 2. And notice there's no x here now, so the limit is just equal to this quotient of derivatives. F prime of 0 is 2, and g prime of 0, well, the derivative of g is just 1, and so when you evaluate it anywhere, it's going to be equal to 1. And so indeed, we see that we get the right thing. We get the 2 that we were expecting. Remember, if we look at the this is the content of L'Hopital's rule. So maybe let's go ahead and state that. So, theorem. So if f of a is equal to g of a, which is equal to 0, so we're going to be approaching 0 in the numerator and the denominator here, then the limit as x approaches a of f of x over g of x is equal to, and we could just say f prime of a over g prime of a, but more generally, it's equal to this limit as x approaches a of f prime of x over g prime of x, because it could happen that the derivatives are also 0 at that point. That can certainly happen, and it does in many instances. And so this gives us a way of evaluating a limit. If I want to evaluate a limit, which is an indeterminate form, it's equal to 0 over 0, then it suffices to compute the same limit, but I differentiate inside. Okay? And this holds a little bit more generally. So more generally, if f of a is plus or minus infinity, and g of a is plus or minus infinity. And what I mean by that is that the limit as x approaches a of f of x is equal to plus or minus infinity. Of course, it doesn't make sense to really define these quantities like that. But if these limits are true, then you can do the same thing. Then the same limit equality holds. So basically, if you have an indeterminate form, then you can compute this limit by taking derivatives in the numerator and the denominator. So maybe let's clarify what we mean by an indeterminate form. Definition. An indeterminate form is an expression of the form 0 over 0 or plus or minus infinity over plus or minus infinity. So if limit as x approaches a of f of x over g of x is equal to an indeterminate form, we can apply L'Hopital's rule. Okay? That's the whole point, is that if you have this limit and you're approaching 0 over 0, and it also happens to work if you're approaching plus or minus infinity over plus or minus infinity, then you can compute the limit by computing the limit of the quotient of the derivatives. Okay? And this happens to be very useful a lot of the time. So let's go ahead and work a few examples just to see how this actually plays out when you're doing these computations. So I hinted a long time ago at this particular limit, and now we sort of have the ability to compute it rigorously. So let's compute the limit as x approaches 0 of sine of x over x. Okay, well, we know that we should get 1. That was what this special limit was equal to, so we want to make sure we're actually going to see that when we do this calculation. So the way that I like to write these out is to say that the limit as x approaches 0 of sine of x over x, this is equal, and then I put a little LH to denote that between these two equalities I'm applying L'Hopital's rule. So this is equal to the limit as x approaches 0. Sine of x, I differentiate that. That's cosine of x. And then x just differentiates to 1. And cosine of x is continuous at 0. It's just equal to 1 at 0. So this is equal to 1 divided by 1, which is 1. And there we go. We've shown, using L'Hopital's rule, that this limit is equal to 1 over 1. And we should have, before we started this, sort of said we have an indeterminate form, and so L'Hopital's rule applies. Okay? So let's go ahead and do another example. I had my notation slightly wrong here, so I want to make sure that I'm using familiar stuff for you guys. So limit as x approaches 0 from the right of x times the natural log of x. Okay, so I've got this function. Let's go ahead and see what kind of form we get. Well, if I plug in 0, and as I approach 0 from the right, I'm going to get 0 for x. And then let's remember what the graph of the natural log of x looks like. If I were to draw that over here, it has a 0 when x is equal to 1, so the natural log of 1 is 0. And then it shoots down to negative infinity as you approach 0 from the right. So this is like 0 times negative infinity. Well, that's not quite one of the forms we have up here. So maybe we need to think about a creative way to rewrite this. And one sort of thing you might sort of think to yourself, thinking emoji to yourself, is that 0 is equal to 1 over infinity. So idea, 0 in quotation marks, because this is not rigorous, but 0 is equal to like 1 over infinity. Okay? Or infinity is equal, in quotation marks again, to 1 over 0. Okay? So with this in mind, maybe there's a way to rewrite this so that the form I get out is one of these indeterminate forms that will allow me to apply L'Hopital's rule. And indeed, we can do that. So note that x is equal to 1 divided by 1 divided by x. So all I've done is I've taken x, I've taken the reciprocal of it and made it 1 over x, and then I've taken the reciprocal of that and flipped it back again. Okay? And if you don't believe me, you can simply just multiply by 1 over x on each side of this expression, and you'll see that you do in fact get the same thing on each side. Okay? So all I've done is taken x, flip it again, and I can use that to rewrite this expression. So limit as x approaches 0 of x times the natural log of x. This is equal to the limit as x approaches 0, and I should say from the right, of the natural log of x divided by 1 over x. Now I have a quotient, and notice what happens as I approach 0. Natural log of x goes to negative infinity, and what does 1 over x do? 1 over x goes to infinity as well as I approach from the right. So the graph of 1 over x as I approach from the right looks something like this. Okay? So 1 over x, natural log of x. So as I approach from the right, I blow up to positive infinity, and so what I'm getting here is negative infinity divided by infinity. And I do have an indeterminate form, so I can apply L'Hopital's rule. So let's go ahead and do that. This is equal, by L'Hopital's rule, to the limit as x approaches 0 from the right. I need to differentiate the natural log of x, so this is 1 over x, because the derivative of natural log of x is 1 over x. And then the derivative of 1 over x is negative 1 over x squared. So remember, 1 over x is equal to x to the negative 1. And so when I apply the power rule, I get a negative 1, and then I drop the negative 1 to a negative 2 by subtracting 1 in the power. Okay? Now, we just need to simplify this. So what is this equal to? This is the limit as x approaches 0 from the right. And now let's do the sort of same thing that we did up here. Let's flip this 1 over x squared back up into the numerator. So this is going to be 1 over x. That's this guy. And then when I flip I have a 1 over negative 1 over x. That's just going to turn into negative x squared. Okay? So again, all we're doing is just flipping the fraction and then flipping it back to get it into a normal sort of expression in the numerator. And now we simplify this. This is the limit as x approaches 0 from the right. This is just negative x, because negative x squared divided by x is just x. And now we have a continuous function at 0, and so we get 0. Okay? So that's how you can do this sort of limit with L'Hopital's rule. I want to do one more kind of example to show you the range of limits that you can compute with this. So last example. So let's compute the limit as x goes to infinity this time of x over e to the x. Okay, so our form here, well, as x goes to infinity, I get infinity divided by And then what's e to the infinity? Well, it's just infinity as well. As x gets larger and larger, e to the x gets larger and larger. So this is going to be infinity over infinity. And we can apply L'Hopital's rule. So let's go ahead and do that. The limit, as x goes to infinity, of x over e to the x. This is equal by L'Hopital's rule to the limit as x goes to infinity. The derivative of x is just 1. And the derivative of e to the x is e to the x. And so, as x goes to infinity now, e to the x goes to positive infinity, but 1 over a number which is really, really big and getting much, much larger. This just approaches 0 as x goes to infinity. And one way you might think about this is e to the x grows much faster than x does. So if you think about x equal to 10 or 100 or 1,000, well, e to the 10 is a lot bigger than 10. E to the 1,000 is magnitudes bigger than 1,000, and so on and so forth. And so as x shoots off to infinity, e to the x is blowing up much, much faster than x is. And so it sort of gets to infinity faster than x, which is why this limit is equal to 0. That's a very sort of informal way of saying that, but we might say that x is dominated by e to the x. E to the x grows much faster than x, okay? And in the previous example with x times the natural log of x, well, natural log of x is shooting down to negative infinity, but x itself sort of dominates the growth of log x. Log of x is not a fast-growing function. Its derivatives are quite small. And so as x approaches 0, x sort of gets to 0 before natural log of x blows up to negative infinity. And so natural log of x is dominated by x, and that's why this limit is equal to 0. Natural log of x sort of doesn't do its thing as fast as x does its thing. Again, very informal, but maybe a helpful way to think about that. And there will be a couple of problems in your written homework that explore that a little bit more. Okay, so this is L'Hopital's rule. This is the last of our applications with the derivative. And in the next lecture, we're going to begin the second half of this course, which is integral calculus, and looking at some very interesting concepts in how to essentially do derivatives, but in reverse. Okay, so see you all in the next lecture.